All right, we are continuing on with talking about chemical reactions. Um, this segment of our unit on chemical reactions is about stoichiometry. Stoichiometry. Again, I'm sorry, a lot of words and vocabulary in science is not English. It comes from Greek or Latin root words. So this is very much a Greek-Latin sort of thing. We are going to use what we know about balanced equations to be able to solve products, so we can to solve problems where we can predict the amount of products we can make and the amount of reactants we need to make a certain amount of products. This is very important in industry because we want to sort of minimize the amount of reactants we use to maximize the amount of products we can make, right? If you're making a cake, you don't want to use 6 eggs when really you only need to use 2 eggs, that kind of thing. All right, so this is what you should be able to do. And again, you need to be able to ask yourself, can I do this? And if the answer is no, then you need to study it some more. You need to ask for some help. Come to see me. So you need to be able to use a balanced chemical equation and know that the coefficients found in the balanced chemical equation are the moles of each species in the equation. The moles are very important because they set up ratios among the different species. Okay? You should know how to balance a chemical equation, but if you're still having trouble with that, please come to see me. All right, so the word stoichiometry comes from 2 Greek words. First word, stoichion, is the Greek word for element, right? Our periodic table of the elements. So our hydrogen, our sulfur, our nitrogen, those are elements. The word stoichion just means elements. And the second word, metron, which you've probably seen similar things, that meter stick is a similar root in there. Geometry, very similar words, and these mean in Greek to measure. Now, I've told you before that if you start sort of memorizing some of these Greek root words, when you begin to see them more and more in academic English, then it will become easier for you to determine and remember the meaning of some of these really difficult words. But if we learn a little bit of basic Latin, a little bit of basic Greek, our vocabulary and our knowledge of academic vocabulary can expand so much. So it's so important to learn what these are. So a formal definition of it is to study the quantities. The word quantity means how much or how many as it relates to chemical equations. So how many products we have, how many reactants we have, what are the relationships between certain reactants and certain products that are made, that kind of thing. Chemistry is called a quantitative science, meaning that we can measure it and count. Some sciences are not quantitative, like chemistry and physics are certainly quantitative. Something like biology, which I teach and I really enjoy, is not as quantitative as chemistry is or physics. So we've spent a lot of time on naming, on atoms, of writing and balancing chemical equations, but we need to know exactly what does it mean at a fundamental level when we have this kind of equation. So what's this saying? So we have some nitrogen gas. Remember, nitrogen is one of our diatomics. It follows the rule of 7, and we're mixing it with some hydrogen gas. And if you put these with some, mix them together, we can make, this is ammonia. Ammonia. I always get ammonium and ammonia confused, but ammonia is NH3. Okay. So one way that we can look at this is by counting the molecules that are there. So if we look at it, what does diatomic nitrogen mean? Well, it means that we have 2 atoms of nitrogen that are bonded covalently together. And then think about how many this is. So we've got, this is 1 diatomic hydrogen. But to balance it out, we need to put a coefficient of 3 on the front. So that means that we have 3. And at the end, we make 2 molecules of ammonia. But notice, right, everything is balanced here. We start with 2 nitrogens. We end up with 2 nitrogens in the product. We start with 6 hydrogens in the reactants. We end up with 6 hydrogens in the products, right? We can look at this in terms of mass, pure mass. Okay? The mass of diatomic nitrogen, 1 mole of diatomic nitrogen, 28.02 grams. Hydrogen, we have 6 of them, so 6.06 grams. And then we add them, this is it, right? These are the same, right? The number of atoms in the reactants and the products will be the same, and the mass in the reactants and products will be the same. This is called the law of conservation of mass. Nothing is, when we undergo a chemical equation, it may look like something new has been made. In a molecular sense, something new has been made, but in a chemical sense, what's really happening is just the atoms are being rearranged. So no mass is being lost. All mass is conserved. We can also look at this in terms of moles. Now, moles are related to a set number of atoms, and atoms are different sizes, so it's not going to be 1 mole to 1 mole because they're related to different numbers, the 6.02 times 10 to the 23rd atoms and molecules. But what it will do is set up a ratio. So the coefficient, the number in the front, is called a coefficient, relates to the number of moles that are there. This tells us that we have 1 mole of nitrogen gas plus 3 moles of hydrogen gas. In case you're wondering, we can just write it in a short form way of MOL. You can't just write it as M because M means something different. It relates to solution calculation. So we don't use that in chemistry. If you want to talk about moles, to do it in short form, just MOL is fine. And that will give us 2 moles of ammonia. Okay. These kind of molar ratios and how they're related to mass, the mass part is very important too, is what we'll focus on in this little subunit. So the coefficients, right, again, those are the numbers out in front of the different molecular species in a chemical equation, represent a ratio between the products, the reactants and the products. So in this, we can describe it in many different ways. We can set up many different ratios with those numbers. Again, in the red box, those are the coefficients. 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 So if I want to compare nitrogen gas to ammonia in the product, I can set it up by a 1:2 ratio. It's this ratio. If I want to compare hydrogen gas nitrogen gas, it becomes a 3 to 1. Or if I want to compare, we can compare products to reactants. We can go the backwards way as well. So if I want to compare ammonia with hydrogen gas, I can do that as well. So I can set this up in any way I want. This allows us to compare and make pretty accurate predictions about how many moles of reactants are needed to make how many moles of product. All right, so what do we actually use this for? Well, if we want to know, so we have 3.86 moles of potassium and they react completely with excess water. What does that mean? Well, excess water means that all the potassium is going to be used up in the reaction, but there's going to be some water left over at the end of the reaction. This gets into the idea of limiting reactants. We are going to look at that maybe starting next week. But for now, just to understand what this means, it means that there'll be water left over at the end of the reaction. Not all of the water is going to be used up in the reaction. So how many moles of hydrogen would be produced? So the first step you need to do here is you need to be able to write out the chemical equation. So potassium, water, and sometimes a good trick, as I showed you the other day, is to change water into hydrogen hydroxide because it can help you, especially if you have other hydroxides and as a polyatomic, it can help you to balance them out. It doesn't change the number of atoms that are there. It doesn't change it, but it can help you with balancing purposes sometimes if you consider water as a hydrogen hydroxide. It's just a tip. You don't need to do it, but sometimes it can make things a little bit easier. You can separate a hydroxide group from an additional hydrogen. I'll show you that. So we would expect that to make potassium hydroxide and hydrogen. This is very similar to the reaction that we did in class. We didn't use potassium, but I showed you what happens with sodium in water. It's quite a violent reaction. Anyway, so we got some potassium, and this is what still H2O, but if you write it this way as in a hydrogen hydroxide, it can help you balance this out. It kind of separates the hydroxide group, potassium hydroxide. See, then you can just worry about balancing hydroxide plus hydrogen. All right? So we got step 1, write the equation down. Step 2, balance the equation. If your equation is not balanced, then you won't have the correct coefficients. If you don't have the correct coefficients, you cannot set up any ratios that are going to accurately solve the question. So it's of paramount importance that the equation be set up properly and be balanced. Okay, so we've got potassium, potassium, that's balanced. I've got a hydroxide and a hydroxide, I do that, so it's balanced. Hydrogen, hydrogen, it's not balanced, so what am I going to do? Well, if I throw in a 2 there, then I have to throw in, so first I want to balance out my hydrogen, so I throw in a 2 here to balance out my hydrogens, but then I've added an extra hydroxide, so I need to balance out the hydroxides on this side. Then I've added a second potassium, so I need to go back and add a second potassium there. So convince yourself that's balanced. Okay, so now what do I do? What I need to do is I always need to start from what I have, which is kind of what I know, to what is unknown, which means what do I want? So I have moles of potassium, and I want to find out how many moles of hydrogen gas will be produced. So, right, this is what I have, what I want. Okay, so I set it up. So here's what I know. I've got this much, and now I'm going to set up a ratio. Okay. So we want, at the end, we want to know moles of hydrogen gas, so it needs to be at the top. We want moles of potassium to cancel out. So on the second ratio, make sure you put it on the bottom, so that will cancel out. And I'll be left with moles of hydrogen gas, which is what I want. So you just have to set it up. So how many moles do I have in the equation? Between 1, and then for potassium, how many moles do I have here? 2. Okay? That nicely cancels out moles of potassium. And then it's just, what's the calculation? It's just 3.86 divided by 2. Gives us 1.93 moles of hydrogen gas. Remember, Mr. Harrison would like to see your answer in a box. Please and thank you. Okay, so there's one more example here. So we've got how many moles of aluminum, or aluminium, however you want to pronounce it, aluminum will react with 0.512 moles of hydrochloric acid. Well, your first step, you need to write an equation to do it. So we've got aluminum, hydrochloric acid, which is just the same thing as hydrogen chloride. Into that. I've told you that for this course, we don't really need to know about acids and bases and how to name them. So something like this comes up on a test. I don't expect you to know it, and I will tell you about it. Okay, so this will just be a single replacement reaction. So we expect the product to be aluminum chloride and hydrogen. Remember, hydrogen's a diatomic, so that'll be hydrogen gas. So now we need to write it out. So many moles plus hydrochloric acid, hydrogen chloride. Remember, aluminum has a charge of +3, chlorine has a charge of -1. So to balance out the ionic charges, we're going to need to have 3 chlorines plus diatomic hydrogen. Are we finished? No, because we need to make sure that everything is balanced out properly. So, I've got 1 aluminum, 1 aluminum. That's fine. I've got 1 hydrogen, 2 hydrogens. Uh-oh. I've got 3 chlorines, and I've got 1 chlorine. So, the best thing to do is always leave your hydrogens and your oxygens, and you have that right to the end. Try and balance everything else out first, and leave those to the end, because they can sort themselves out. So what I do here is I would put a 3 in front here to balance the chlorines out. Now, what's that going to mean? So then I will have 3 hydrogens on this side, but only 2 hydrogens on this side. So how can I get this to be 3 and 3? Well, what I can do, that doesn't help. What I can do is I can put 1.5 here, 1.5, because 1.5 multiplied by 2 is 3. So that does become balanced. The only thing to remember, though, is that we can't have a fraction. There can't be a piece of an atom. That doesn't make any sense in chemistry. Mathematically, it makes sense, but in chemistry, a half of an atom doesn't make any sense. But luckily, mathematically, there's a way that you can fix that. If you go back and multiply everything on the equation back through by 2, it'll be balanced, and it will solve the problem with the fraction. So remember, this one had a 3, this one had a 1.5. So if I multiply everything by 2, so this will become 2. Multiplying 3 by 2, this will become 6. There was nothing here, so this will become a 2. And then 1.5 times 2 will be 3. Okay, and then if you check it, it should be all perfectly balanced. So 2 aluminums, 6 hydrogens, 6 hydrogens, 6 chlorines, 2 times 3 is 6. So that's all perfectly balanced. Remember, it's Very, very important to have everything balanced out because these will tell you the mole ratios. If you don't have the proper ratios down, you won't get the correct answer at the end. Okay, so next we go from what we have to what we want. What we have to what we want. So we are told that we have this much hydrochloric acid and we want to know moles of aluminum. These two are what we're going to compare. So set it up. So start with what you have, 0.52 moles hydrochloric acid. You want this to cancel out, so you're going to put moles of hydrochloric acid on the bottom. You have 6. And then what you want, you're going to put at the top. You want moles of aluminum. Okay? 2/3. If you want to simplify the fraction to become 1/3, that's fine. That's the same relationship. Okay? Cancel. That will cancel. Leave us with that. If you have any questions, please let me know. Right? I'm available now Thursdays. There's tutoring after school on Thursdays. There could be after school tutoring on a Monday if you really wanted to as well. And then I'm also available to come to study hall whenever you need me to. Okay? Please study and practice.